Okay, beginning with question number 1, we might not always do these things in sequence, but let's begin with that. Complete the table below, which is writing out straightforward electron configurations. Very standard question in exams, and looking at your past examination papers, you are virtually guaranteed a question like this in every single exam, and it is a very straightforward question to answer. When you answer this, you should look at your resource sheet and have your periodic table in front of you. Now to, excuse me, scandium, vanadium and vanadium-3 class. Let's look at where these elements are in the periodic table. Looking at scandium here that I'm pointing to. And what happens with scandium? You've got the inert electron configuration of argon, that's the complete inside shell. Then inside that, of course, you have the hydrogen helium. I've just only taken a section of the periodic table here, simply because we will be just using this part really in the questions, so I didn't need to have all the rest of it in there. So, looking at scandium, here it is. Now, what happens when we fill these periods? You have 2 electrons in the first quantum level, which all go into an s orbital. So it will be a 1s2. Then you have a 2s2. That's when we get from sodium to magnesium. Then you have 2p6. And then after the second quantum level is filled, which happens at argon, 2p6, we come to potassium, calcium, and scandium. When you fill electrons into atoms, the lowest energy orbital is the s orbitals of that quantum level. So you put electrons into the, I missed a period here. So sorry to have caused any confusion. That's why I'm drawing this cutaway section of the periodic table, because above that there's the second period, the lithium, beryllium, boron 1. So this is the third period where sodium starts. So that's the 3p orbitals completely filled up. And then we go on to the 4s here. So that's 4s2, 2 electrons there. And with scandium, 1 electron goes into the d orbitals for the first time. So that will be 3d1. That's the d orbitals of the third quantum level, which come up, which are energetically higher than the 4s orbitals. So that's why they only get filled after the 4s level. So returning back to the previous slide, where I will write this down now, we could write it this way: 1s2, 2s2, 2p6, then we come to 3s, 2, 3p6. Now that's when we've got to the argon configuration. Thereafter we have a 4s2 and a 3d1. So that's the stable, that's the electron configuration of scandium. Now, it's also acceptable, definitely, to write this in this way: argon, because that is the completed inert gas electron configuration that's inside of the valence shell, argon, and that, if I draw that in a different color maybe, that argon here comes up to this point. That's the sort of argon part of it, where the 3p shell has been filled, and thereafter we've got 2 electrons in the 4s, so I can go 4s2 and 3d1. Okay, I can put that in that way. Now, does anybody have any question about how I arrived at that? We'll then look in a very similar way at vanadium as well. And then we'll get on to vanadium 3+, which brings up something else. So, any questions, please, anybody? The quicker you answer, interact with me in this way, the faster we can go through, because I know that people have understood or they haven't understood, and if I need to explain something again or in another way. No, I take it that that's okay then. And then let's look at vanadium. Again, just like the previous one, and there'll be plenty of questions for you to practice these sorts of things with later. We are talking here about vanadium, which is the, over here, the symbol V, and that, let's look at its inert gas, its electron configuration. It will have the complete inner shell structure of argon, and thereafter there'll be 2 electrons here in the 4s, and then we have 1, 2, 3 electrons in the d orbital. Okay, so let me write that over here. We have 3 in there, so I can go here, and if I write it in the shorthand notation, I could write it as argon, 4s2, 3d3. Or I can put everything else in here that was inside this red square brackets, which is the argon part, and then write 4s2, 3d, not 1, but 3d3, because our vanadium is 2 places further along after scandium, and therefore that completes that picture. I take it then everybody followed that also, and if you've got any question, please ask me now. They're very similar questions, really. One was with scandium, one was with vanadium. Okay? Now I'm going to ask you something else. Let me look at, in this instance, let's say we look at, I use the purple color, and what's this? There. Let's say we're looking at the element chromium. Okay. If I were to write this here, would I be correct to say that chromium has this electron configuration? The inner shell electron structure of argon, followed by, I'm just asking this as a question, 4s2, 3d, this my reasoning, 1, 2, 3, 4, and would that be correct to say 3d4? Would that be correct? Anybody able to answer that? No, says Rose. Any other comments from anybody? No? No? Good. Few people seem to have got this. Absolutely correct. Good one. I was just trying to see how well people had understood this from what you had done at school, and I'm pleased to see that that was a generally very satisfactory demonstration of people's understanding of this. Absolutely. So your answer to this was correct. That's not going to be like that. Chromium actually has, the inside part is the argon part, 4s1, 3d5. Okay. And now you can type in there, what is the other element in this D block here, or the transition metals as we call it, where you see a unexpected result like this. You know the normal way would have gone, 4s2, we add electrons to the d orbitals. There is, but here, what happened? It became a 4s1 and a 3d5. Everything else kind of works normally. But there is one other one here where this unusual thing happens. Which one is that? Yes, Rose, absolutely correct. Good to see that again. The other one is copper. So here we have this one here. So if you draw the electron configuration of copper, that would be the argon configuration. And then we'd go, what happens? With copper, you'll normally otherwise have had a 4s2, and then you would have had 1, 2, 3, 4, 5, 6, 7, 8, 9. But it becomes 10, and you will have 1 electron left. So you will have copper, that's the inner shell structure of argon, and 3d10, not 4s. This is the correct one for chromium, and that's the correct one for copper. It's not going to be 4s2 3d9. So the easy way to remember this, it's two of the things that starts with C, chromium and copper. Forget about the cobalt, okay, that's all normal with cobalt, the way the electrons get distributed. But with chromium and copper, the 4s2 switches over to a 4s1 with that extra electron going into the d orbital. Right. Have I clarified that? Does anybody have any question? Anybody who wasn't quite clear about that before? Any question from there? No, this is the time to ask, and that's why you're here, to improve your understanding. So don't just sit there if you don't understand something. Go right ahead and ask. Right? That was a particular point I wanted to go through with you. Hence my explanation there. Now, let me go back to our slide and look at the other next ion that we had to answer this for. Vanadium 3+. Now what happens when we look at something like vanadium 3+? I'm going to do this one, say in it's a green color. Vanadium 3+. Now, when you start to remove electrons from these atoms, remember this. The first electrons that get removed are from the s orbitals, right? When you add electrons, you go into the s orbitals first and then into the d's. But what happens is the actual totally detailed explanation of that is a mathematical result that's quite complex to do with the interelectronic repulsion that arises. The end result of that whole process is that the d orbitals are lower in energy than those electrons in the 4s when it comes to removing those electrons. So the 4s electrons come off first before you remove the electrons in the d orbitals. So what happens here? Those two electrons, when we form vanadium 3+, which was here, the first two electrons to get removed are the 4s electrons. And then vanadium, it's 3+ now, so it has 3 electrons that were normally there. 2 have come off here, and 1 more to come off. It'll be end up with 2 electrons in the 3d level. So it will be the argon configuration, right? The argon configuration on the inside. And after that, of those 5 electrons that it had in the outer shell, 1, 2, 3, 4, 5, vanadium, 3+, you're going to be left with 3 electrons. 2 went away from there, 1 goes away from here. You end up with 2 electrons in the 3d level. So it will be the argon configuration and 2 electrons in the 3d level. That's the what the vanadium 3+ is going to be in terms of its electron configuration. Okay, argon 3d2 is how we would write that answer. Or you could fill in what the argon, that inner argon configuration is, or you could write it like that. Okay, So those are the answers to question number 1. Now, before we move along to the next thing, anybody either a question directly about any of that or anything else it reminded you of that you might not have understood completely before? Ask me now. No? Somebody is typing something. There's a question coming through, I think. Right. Having not studied this standard just yet at school, can I have a quick rundown of what orbitals and d orbitals are? Okay. Okay. D orbitals. Okay. Let me explain that quickly, certainly. Now, what happens is this. When we have the different quantum levels in an atom, then the lowest energy that electrons can occupy is in the first quantum level. And then we have the second quantum level. I'll draw it with a bit of, they're not drawn to scale, but I'm just drawing it with some space between them for a good reason. Those are the quantum levels in an atom. You would have done some of this in your level 2 work, okay? The quantum level 1, quantum level 2, quantum level 3, quantum level 4. Now, the first quantum level can have only one type of orbital, and that's an s orbital. So we can write it as the 1s orbital. Right. When we come to the second quantum level, that has two types of orbitals called s and p's. So it will have a 2s orbital and it will have 3 lots of 2p orbitals. I'll just draw them off to the side here, just to avoid some clutter. 3 lots of p orbitals, 3 lots of 2p orbitals. So sometimes we write them as 2px, 2py, and 2pz. Okay. So understand what's happening so far. The first quantum level has only one type of orbital, that's an s. The second quantum level has a s orbital of the second quantum level. That's why we call it 2s. So s's always come in lots of 1. And the other type of orbital is the p orbital. And the p orbitals come in lots of 3. So we have 2px, 2py, and 2pz. That's because their orientations are like 2 lobes along an x-axis, a y-axis, and the z-axis. Hence, the 2p, x, y, and z. And the s orbitals have a spherical symmetry around the nucleus. Rosie, is that making sense so far? Right? Okay. Then when we come to the third quantum level, understand what sort of situation we are going to have. I told you that everything starts off with an s orbital. So every quantum level has to have its s orbital. And there's only one of those. Then there'll be 3 lots of p orbitals. Right. And each time we go up a quantum level, there's a new type of orbital. So it goes s, sp, and when we come to 3, we have spd. So, and the d's, I think you would have guessed it, s's come in 1s, p's come in 3s. What's the next odd number? D's come in 5s. So we have our 3s. We have one lot of a 3s orbital. Higher than that in energy, there'll be 3px, 3py, and 3pz. 3px, 3py, and 3pz. Okay. Now, I told you that belonging to the third quantum level, there's going to be another type of orbital, which is called the d orbitals. And like s's in 1s, p's in 3s, d's coming 5s. So there will be 5 lots of d orbitals. But the thing is, these d orbitals are going to be quite a lot higher in energy. I'm not drawing this to scale, but I'll draw them here. There's the 5 lots of 3d orbitals. I'll just write it like this. 5 times 5 lots of 3d orbitals. There we are. That's what that's saying. Now, they are higher in energy than the s orbital of the 4s. So, there's the s orbital of the 4th quantum level. So, this is why, and each orbital can accommodate up to 2 electrons. So, here you put 2 electrons in the 1s. That's how I'll say which elements these are as I go through it. First quantum level, hydrogen, helium, 2 electrons. One here, one with the opposite spin in the same level. We go to the second quantum level now. Whenever you start a new quantum level, you start a new period in the periodic table. So over here, when we start filling the second quantum level, we begin the second period in the periodic table. I hope you're looking at a periodic table that you printed out as I speak here. And when we start the second quantum level, we start with lithium. So lithium, beryllium. Then we fill up its 2s orbitals. Then we go to boron, which is where we start filling the p orbitals of the second quantum level. So we have boron, and after boron comes carbon, and then comes nitrogen. And you put 1 electron in each of them before any of them has 2 electrons in it. Why? Because electrons repel each other. So then, when we come to oxygen, for the first time, a second electron goes into a p orbital that already has 1 electron. Then, after oxygen comes fluorine, and then after that comes neon. Okay, and our 2p orbitals have been filled. Our second quantum level is completely full. Remembering this is actually a good thing. This relates to some of the things coming up very directly. Third quantum level, sodium. First electron goes in there. And magnesium, the second electron goes into the third level. Then we go 3px, 3py, 3pz, which is all the way through from aluminium through to argon. Our third quantum level is filled, and whenever we complete a set of p orbitals, you finish that period in the periodic table. So we are at argon here when the 3p is filled up. Now, the next electron with potassium, it doesn't go into 3D because that's high in energy. Electrons are lazy. They fill in things from the lowest energy upwards. So the next electron for potassium goes into a 4s, not into a 3D. So that's why that will be a 4s1 in the outer shell. And after potassium comes calcium, and calcium will have a second electron in that same s orbital. And then after that comes scandium, I think, where we start off putting electrons into the d orbitals. Okay, Rosie, is that making sense? That's a review of what is called the Aufbau principle. Okay, right. Anybody else, any question? Or otherwise we can move on, having reviewed this, into the next part, which all of these things produce this type of information. How are we doing on time? Okay. Now, question number 2. By the way, there will be plenty of other examples for you to practice this with. So, if you didn't get everything correct, then your opportunity is to redeem yourself. Discuss the electronegativity data for the pair of particles below. Again, very common types of questions, as indeed is question 3. Now, atom, oxygen, scandium, electronegativity 3.44, 2.55. Now, first of all, understand what electronegativity means. Electronegativity is the electron gaining ability of a species. If you're not sure of that, make a note of that. What's electronegativity? It is a numeric indicator of the electron gaining capability of a species. Now, which types of things is it that gain electrons? Metals or non-metals? Clearly, it is non-metals that gain electrons. So a high electronegativity indicates a highly non-metallic nature. So the more non-metallic an element is, the greater will be its electronegativity, and the more metallic something is, it will tend to lose electrons, not to gain electrons. It will have a lower electronegativity. So it's hardly surprising that oxygen has a much greater electronegativity, which is oxygen is a very powerful non-metal, whereas scandium is a metal, and it's reasonable to expect these. Now, when we discuss something like this, we need to look at their positions in the periodic table to then answer it in terms of their atomic structure. So let's look at our periodic table and focus on the positions of oxygen and scandium. Okay, and then you should see the answer quite readily. Over here we have our oxygen. Oops, it's not even there because I told you I began drawing it from the third period because I was really focusing on these transition metals here. But oxygen is of course above sulfur, it's over there. Let me just write that there, that's oxygen. And of course here's our scandium over here. Right. Now, discuss it. Oxygen can gain 2 electrons to achieve a completely filled outer electron shell. So therefore, it will become the stable inert gas electron configuration of argon. That is why it's got a high electronegativity. On the other hand, scandium cannot complete an electron shell. How can it achieve a stable inert gas electron configuration? By losing these outer shell electrons, and you'd expect it therefore to have very low ability to gain electrons. Now, you can answer it in terms of that, and you could also word it this way. The electron gaining ability of a species depends on the nuclear charge, which of course is greater here. But what happens? In scandium's case, it's situated further away because the electrons are in a shell that is an outer shell that is further away from the nucleus. So again, that makes sense because with oxygen, they are much closer to the nucleus. Right. So I would give that answer in this way. The oxygen can achieve or attain a completely filled outer electron shell by gaining 2 electrons. This makes it highly electronegative. Scandium, on the other hand, can achieve a completely filled, a very stable, completely filled outer electron shell only through losing electrons. So it will be expected to have a low electronegativity. Then you could say something more. In the case of oxygen, the outer shell electrons are much closer to the nucleus. In the case of oxygen, the outer shell electrons are much closer to the nucleus. It's way up there. So, the nucleus, obviously the nucleus is positively charged, is able to exert a greater force of attraction to gain electrons into its outer shell. So, the nucleus is able to exert a greater force of attraction to gain electrons into its outer shell. Because the distance is very small. In oxygen, where are the valence electrons? in the second quantum level, okay, or the second shell, if you like. On the other hand, with scandium, if you look at a complete periodic table, by the way, oxygen has got an atomic number of 8, which means 8 protons in its nucleus. Look at scandium. Its atomic number is 21, right? That's that sequential number there, atomic number 21. So our scandium has got 21 protons. Oxygen's got only 8. So if you just thought about only that, you'd think, now scandium should actually then attract electrons much more strongly, shouldn't it? But that's not the only factor. With scandium, outer shell electrons are situated so much further away, and there is a greater shielding effect, because don't forget, between the outer shell electrons and the nucleus, there is another whole shell of filled electrons. So therefore, the outer shell will be somewhat shielded from the full effect of the nuclear charge. So we've got to explain those factors there. So I would word it this way, the continuation of that answer. Even though a scandium nucleus has many more protons, put within brackets 21, even though a scandium nucleus has many more protons, within brackets 21, compared to an oxygen nucleus, within brackets 8, with scandium, the outer shell is much further away from the nucleus. The outer shell is much further away from the nucleus. Also, with scandium, there are more filled electron shells. There are more filled electron shells between the outer shell and the nucleus. And then say the combined effect of greater distance and increased shielding effect, the combined effect of greater distance and increased shielding more than offsets the greater nuclear charge. More than offsets the greater nuclear charge and makes scandium less electronegative than oxygen. Okay. Now, that is the most complete way that you can answer that question. That's perhaps now for just this one particular standard. If you look at your exam paper, they suggest that you take 60 minutes to answer the questions in there. Sorry, 45 minutes. Now, if you divide that up between the 3 questions, it's not necessarily equal, but close to 15 minutes on each of those 3 questions. So you might not have that much time to go into such detailed essay writing, but I'm giving these answers to you in even more detail, and you can certainly condense it appropriately, so that A, to improve your understanding, B, if that was on a significant part, rather than having 3 parts, if that was only 2 parts of that particular question, then obviously they are going to expect more detail, and then you would go into the full unabridged version. Okay, but mainly it is so that you understand this. Later on, when I do similar questions, I won't go to the same detail, because we'll look at the answers and we'll move along to cover more questions. Now, anything further anybody wanted to ask, or if they like to see what was right or wrong, or how they could improve their own answer, please ask me now. I can give you the microphone if you want to read out what you had written. Maybe you didn't get a chance to do that because you only started today, but in the subsequent days with the homework, you might like to do that. Anybody saying anything? No? Should you also include electron configuration for reference during the discussion? You could, you didn't need to, but if you didn't, then make sure that you point out, like what I did, oxygen, number of protons, 8, scandium, number of protons, 21, right? And that the scandium had more filled inner electron shells for the shielding effect. Okay. But otherwise, you could certainly put that in, and then, yes, you can certainly do that. The main thing to get the complete answer, like the excellent standard that you're looking for, obviously, is to cover the 3 points and how they interact and comparatively and produce the end result. All of these types of questions, really, we know the answer, the ultimate situation, and then we are sort of going backwards and justifying it. So what are these 3 factors? The nuclear charge, the distance to the outer shell electrons, the valence shell electrons. They are the ones that affect the chemical reactivity and chemical properties of the substance, and the shielding effect. So those are the 3 things. The shielding effect being the effect of the filled inside electrons, the inner shell electrons, that reduces the effective nuclear charge experienced by those outer valence shell electrons. Okay, so you must touch on those 3 factors and give the comparison of those 3 between the 2 species. Okay, then I think we can move on to the next question. Right. Which was question number 3. Discuss the radii data for the pair of particles below. Now, atom or ion, the radius in picometers. A picometer is a 10 to the minus 12 of a meter, the sort of dimensions of atoms and ions. Okay, so the chlorine atom has a radius of 99 picometers, and the Cl, that's the chlorine atom, and the Cl minus ion has a radius that is much bigger, of 181 picometers. Okay, so it's kind of not quite double, but almost as much. So again, we answer it in a similar way, and this time I won't go into as much detail. I will tell you the essential things, and then if you've got a question, please ask me. Now, chlorine and Cl minus, what do we know about them? They both got clearly the same nuclear charge, the same number of protons in the nucleus. So I'm looking at the 3 things that affect this. Now, electrons are going into the same shell. So the shielding effect is not going to change. We are not going to change the number of inside electrons because that's the same for Cl and Cl minus. What is different between the 2 is what? The inclusion of that extra electron makes the repulsion between the electrons greater in the outer shell, because chlorine has got 7 electrons in its outer shell, whereas Cl minus has got 8. It's got a complete octet of electrons. So the addition of that extra electron creates more interelectronic repulsion, leading to a larger size. The way we look at it is simply, we know the result and we justify it, basically. Because if you look at it, there is a huge difference. So your answer is valid if you pointed out the following things. Cl and Cl minus both have the same nuclear charge. The shielding effect is the same because the electrons are in the same outer shell, occupy the same shell. The outer electrons are in the same shell for both of these. What is different is that Cl minus has an extra electron. The extra electron increases the interelectronic repulsion. That's what you would say. Increases the interelectronic repulsion, and therefore to be more stable, what will they do? It will expand the surface that the electrons occupy, and that makes the Cl minus larger than the Cl atom. Okay. Anybody got any query about that, or want something clarified, or would like their particular answer analyzed? Please ask me. No? Okay.